Hello everyone, welcome back to our YouTube channel. In today's discussion, we discuss a question from the functional analysis part, and this question is asked in the TIFRCAM PhD Mathematics 2026 entrance exam. Okay. In this question, what is given? T is a operator which is defined from the space C101 to the C01, and both these spaces are associated with the supremum norm. Okay, supremum norm is defined in this way. Supremum norm of f is equal to supremum x belongs to the domain 0 1 closed interval modulus of f of x. It is defined in this way. I hope that you all are well acquainted with this definition. Okay, and the operator t is defined in this way. T of f is equal to f dash. Clearly this function is well defined, since the domain is domain contains the set of all functions which are continuously differentiable. Continuously differentiable means the function itself is differentiable and its derivative is also continuous. So the operator t is well defined, though, so there is no problem. In this question we have to check what? We have to check whether this operator t is closed or not. In the second option we have to check that whether this space C101 associated with this supremum norm is a Banach space or not. We have to check these two things. Okay, first we will verify the option 2, then we will move to verify the option 1. Okay, first we will verify the option 2. Okay, our claim is that this space is not a Banach space. Why? We know that the continuous function space C01, this one C01 associated with the supremum norm, it is a Banach space. We all know about this, so I am not discussing about this, but we have to check whether this continuously differentiable functions space associated with the supremum norm is a Banach space or not. Okay, I am saying that it is not a Banach space. Why? Means Banach space means what? Banach space means it is a complete nonlinear space, and we know that every complete nonlinear space is a closed space. If I can show that this space is not closed, then it cannot be a Banach space, because every Banach space is closed. So our target is to show that this space is not closed. Is not closed. Is not closed means what? If a set is closed, means it contains all its limit points. So we will create a sequence. We will create a sequence fn belongs to C101. Okay, and such that fn tends to f. Then we will show that f does not belongs to C1. Means we create a sequence of differentiable functions, but whose limit point is not differentiable. Then we are done. Means it implies that this space C1 does not contains its all limit points. Means there is a limit point which is not in the C1, therefore C1 will not be closed, and this implies that C1 will not be a Banach space. Okay, this is our strategy, and the required function fn is defined in this way. Fn x is equal to square root of x square plus 1 over n. Okay, clearly this function is differentiable. Clearly it is continuous and differentiable for all n greater than equal to 1. Okay, you have to verify it by yourself. From the intuition, it is clear that if you take n tends to infinity, this quantity will go to 0, because square root is a continuous function, so the limit come inside, so this quantity will go to 0. It gives what? Square root of x square, and positive square root of x square is equal to mod x. But this function is not differentiable, but we are taking here the limit pointwise sense, but we have to show that uniform limit also exists, and the uniform limit is equal to mod x, but mod x does not belongs to C1, therefore this set C1 is not closed. Okay, it is our target, but from the intuition, the pointwise limit we are getting mod x, but we have to show the uniform limit. So let us proceed to prove how the uniform limit is equal to mod x. So we start from this expression, modulus of fn x minus mod x. Okay, so this quantity and fn x is defined in this way, so we put this value, and mod x can be written in this form. Why? Because x square root over is equal to mod x. Okay, I hope that you all know this simple meaning of simple expression. Okay, so then this difference can be written in this integral form here. I think I have skipped the modulus here. Here it is, there is modulus. Okay, because after integration you will put 1 by n in place of y, then you will get this term, and if you put the 0 here you will get this term. So this is equal to this, so there is no problem. Then if you will differentiate this with respect to y, you will get this one, okay, by using the chain rule. Then here is I am modulus is left. Okay, keep the modulus. Then here this quantity 1 by 1 over x square plus y square root of this quantity is less than equal to 1 over square root of y. Because why? Because this denominator is bigger than this one. If the denominator will be smaller, then this value 1 by square root of y will be larger. Okay, so therefore we are getting this one. This one, but here you can take the modulus also inside. Modulus you can also take. I think there is no need to take also modulus, because clearly all these quantities are non-negative. Okay, non-negative, because after differentiation we are getting this thing, and this quantity here x is x belongs to where? I have written x is a 0 1 closed interval, so it is also positive, and y is varying from 0 to 1 by n. All these quantities are non-negative, so there is no need to put modulus. Okay, and okay, here, so this quantity is dominated by this, so in place of this we put 1 over square root of y. Okay, this one, and after integration we will get this expression, and after simplification we will get 1 over square root of n. So we are getting this final inequality, and this inequality is true for every n and for the all x belongs to 0 1. So if you take the supremum also, this will hold. Okay, supremum over x belongs to 0 1 close interval, and this supremum value is nothing but fn minus f supremum norm, where f is equal to mod x. Okay, keep it in your mind, fx, where f is equal to fx equal to mod x. Okay, and so it gives if you take the limit on n tends to infinity on the both sides, it will go to 0, therefore the limit value is 0. This means what? Fn tends to f with respect to the supremum norm, but clearly f does not belongs to C1, because f of x equal to mod x is not differentiable. Differentiable at what? Differentiable at x equal to 0. At x equal to 0 it is not differentiable, therefore it does not lie in this space. So we created a sequence in this space, but its limit points does not lie in this space, therefore this space is not closed. Okay, this implies it cannot be a Banach space. So therefore the option 1 and option 2 is false. It is false. Okay, now let us move to verify the option 1. In this option 1, t is defined what? T is a mapping from this continuously differentiable function space to the continuous function space, and both of these functions are associated with both of these spaces are associated with the supremum norm, and the operator t is defined tf is equal to f dash. In this way, here we have to prove that the operator t is a closed operator. We are claiming this. Okay, means option 1 is a true statement. Okay, but before going to prove the closure operator, first of all we have to know about what is the definition of closure operator. This is the definition of the closure operator. If x and y are Banach space and dA is a subset of x, dA means a domain of A. Okay, domain, because we do not know whether the whole x will be its domain. Suppose dA is a subset of x and it is the domain of the operator A. Okay, and y is a Banach space, then the operator A is called a closed operator if for any sequence from the domain of A, if we take any sequence from the domain of A such that any sequence fn such that fn converges to f in x. In x means with respect to the norm associated with x, okay, and afn converges to g in y means afn converges to g with respect to the norm associated with the Banach space y. Then it will if it implies that f belongs to dA and af is equal to g, then it is a closed operator. Means if you assume these two things should imply this thing, then the operator A will be a closed operator. So in our case the operator A is equal to T, and the x and y are the Banach spaces, means this one. I have already told that when the continuous function space associated with the supremum norm is a Banach space, but C1 is not a Banach space. Therefore our dt is the C1 space, C1 associated with the supremum norm. It is the domain of T, okay, and clearly dt is a subset of x, okay. So to show the operator T is closed operator, we have to take what? We have to take these two things, these things and these things. Then we will prove that it will true and it will true, okay. So we will take a sequence fn in the domain of dt such that fn converges to f in x. In x means what? With respect to the supremum norm. And tfn converges to g in y, and y is also associated with the supremum norm, means it is also associated, this convergence is also with respect to the supremum norm, means fn converges to f uniformly and tfn also converges to g uniformly. These two things are true. Then we have to prove that f belongs to dt and tf is equal to g. If we will prove these two things, then the closeness the operator T will be proved, okay. So let us move to prove these two things. We have to show that f belongs to dt. Dt is what? C1, means we have to prove that f is continuously differentiable. First our target is this one, and in the second we have to prove that tf is equal to g. Tf is defined what? Tf is equal to f dash, this one. But to provide a meaning of this, initially we do not know whether f is differentiable, but if we can show that f belongs to dt, then it is differentiable, then this makes sense, okay. First we have to prove that f belongs to C1 space, and we have to in another step we have to prove that f dash is equal to g. We have to prove these two things, okay. So given what? Fn converges to f in x and tfn converges to g in y, means fn converges to f in x what? Means with respect to the supremum norm, and we know that x and y are Banach space, so these things contains their limit points also. Since g and x are the limit points of x and y respectively, therefore x belongs to f belongs to x and g belongs to y, because x and y are the Banach spaces. So therefore f and g are two continuous functions, okay, since x and y are the nothing but the Banach space continuous function space, this one, so it implies this one, okay. And initially we have also taken that our sequence of functions lie in this dt space. Dt space is nothing but the C1 0 1 associated with the supremum norm, okay. So these functions are differentiable. Each fn's are continuously differentiable. So therefore by using the fundamental theorem of calculus, we can write these expressions. Means that here fn dash has a meaning since fn is differentiable, so it is well defined. So and this can be written in this way, because after integration you will get fn x minus fn0. Fn0 cancel out, so it gives also fn x. So it is equal with this one. So it is coming from the fundamental theorem of calculus. Then our next task is to pass the limit on this integral form. When n goes to infinity, we know that fn converges to f uniformly, means it also converges to pointwise, because uniform convergence implies pointwise convergence. Therefore this will equal to fx and this will equal to f of 0. But here there is a problem. We have to pass the limit inside the integral. There is also no problem, since our fn dash here tfn is nothing but fn dash, okay. tfn is equal to what? Fn dash. Okay, so but we know that fn dash converges to g uniformly. So by using the uniform convergence we can take the limit inside the integral. It is a very nice property in the real analysis. If a sequence converges to some function f uniformly, then the uniform limit helps to pass the limit inside the integration. Okay, so we will use that thing. But before that, since fn dash is equal to tfn, we can write this expression. Okay, and it is coming from this thing. So therefore now we can pass the limit, because since we have fn converges to f uniformly and tfn converges to g uniformly, so we can pass directly here, but directly pass the limit in this expression, and uniform convergence helps us to pass the limit inside this integration also. So after passing the limit we will get this expression. Okay, we will get this expression. Fx is equal to f of 0. Fx is coming when we will pass the limit fnx, and f of 0 is coming when n goes to infinity. Fn0 converges to the f of 0 when n goes to infinity. Okay, so we get these things, and this limit also come inside the integral, and tfn converges to g here, so therefore here g is coming. Okay, so we will get this expression. In this expression, in the right hand side, if you look at the right hand side expression, here f of 0 is a real number, constant, and in this expression the integrand g of y, because I have already told in 1 means here we have already shown that g is a continuous function. So g is continuous, and we are taking the integration, and we know that the integration of a continuous function is always differentiable. So this expression integration 0 to x g of y dy is differentiable. Is what? Differentiable. And this is a constant function, means it is also differentiable, and we know that the sum of two differentiable function is differentiable. So the right hand side is differentiable, but the right hand side is equal with the left hand side function, and left hand function is what? F. So therefore we get that f is a differentiable function. So we can take the derivative on the both sides by using the Leibniz rule. By using the Leibniz rule we can differentiate this integral to term also. Then we will get these things, because the derivative of constant is equal to 0, and the derivative of this integral is equal to g of x. So therefore f dash x is equal to g of x. But g of x is a continuous function. I have already told by 1 in 1 I have already shown that g is a continuous function. Okay, so our f dash is a continuous function, means what? Our function f is differentiable and its derivative is also continuous. So this function lies in what? The dt space, because it is the continuously differentiable function space, and we have already shown that, and f dash is equal to what? Tf. So therefore tf is equal to g is also coming. So we have already we have simultaneously showed that f belongs to dt and tf is equal to g, which was our requirement. So therefore the operator t is a closed operator. Okay, therefore the operator t is here is a closed operator. So this statement 1 is true. In option A it is saying that 1 is true, 2 is false. It is correct one. In option B it is saying that 1 and true both are true. It is false. In option C it is saying that both are false. It is false. In option D it is saying that 1 is false but 2 is true, so it is also false. Therefore only option A is correct option. I hope that you all get it, and see you next time again very soon. Thank you all. Bye bye.